Hello friends, this is Subhashree Panda, 18BEC0571, and I'm from VIT Galore. So the topic which I'm going to present right now is the analysis of a floating point unit from open access journal using the concepts learned in the syllabus, and syllabus as in from the subject computer organization and architecture. And the topic which I've selected, as you can see over here, it is energy efficient floating point unit for multimedia application. So FPU, floating point unit, is a core of all the modern DSP processors to process the floating point information of multimedia applications. And this article presents energy efficient architecture to perform 32-bit floating point arithmetic operations, and the presented architecture has been designed by considering 32-bit single precision IEEE 754 standard to represent the floating point data, and also it describes how the arithmetic operations they are conducted and performed. The proposed FPU takes the data called operands to be operated on and a code that indicates which operation to be performed and computes the results. The proposed architecture has been implemented on the FPGA device. The results are verified and the parameters like area and speed has been analyzed. So here comes the very first question, and this is why I have selected the paper and how it is going to relate to my COA syllabus. I have noted it down point-wise. So, the very second question, draw the existing architectures discussed in the paper using some appropriate raster graphics editor software in encapsulated PostScript file format. So, this is actually have drawn using the lucid chart, which I'm going to show you how to do it. It's very simple software, very easy to draw things and just illustrate. It will just take some minutes of your time. And so this is the architecture of floating point unit. Now this architecture of the floating point unit ALU, they operate only on integer values when forced to work on decimal values. It leads to loss of precision and hence the floating point. ALU is designed to represent large range of values. The proposed FPU can perform arithmetic and logical operations on floating point data and support the computation of wide range of digital signal processing application. This is a very important point to remember about this architecture. The FPU considers the operands in the form of IEEE 754 and operational code which indicates operation to be performed and then compute the operands as per the operational code. The FPU shown in this figure 1, as you can see very well over here, could perform arithmetic operations such as addition, subtraction, multiplication, and division. And the FPU architecture has proposed to support the arithmetic computations like addition, subtraction, multiplication, and division. Since the cores are independent to each other, part of the arithmetic cores can be disabled to save the area, power, and also enhance the speed of the core. Required arithmetic cores can be reconfigured easily through the process of cell instantiation, and their results are connected through multiplexer. Arithmetic operations using the proposed architecture core can be processed in 3 stages: pre-normalized, arithmetic core, and post-normalized. Pre-normalized, what they do is that the operands are represented as core understandable format, that is IEEE 754. Arithmetic core instruction level arithmetic operations can be performed, and post-normalized results are normalized and represented into supported IEEE standard, and common pre-normalization and post-normalization core were not used all normalized operations because of the data sizes, clock speed, and data intensive computation requirements. Now, next, there are many architectures regarding this unit, whichever I have selected right now is they have taken one architecture of FPU, The other one being the architecture of multiplication operation, and this one is architecture of division operation. So, as I have described above, the arithmetic operations on floating point numbers consist of addition, subtraction, multiplication, and division. Addition or subtraction of two numbers requires the alignment of radix point and make the exponent of the numbers equal and then perform the required operation with mantissa. The alignment of radix point is made by shifting the mantissa of one operand while its exponent is adjusted until both the operand's exponents become equal. And the mantissa alignment of the operands must be done prior to the operation performance. After the mantissa adjustment, the operands are added or subtracted, and then the result is put forward for normalization. The result is normalized using shift and rounding control methods, and then normalized results are transferred to memory. The architecture of the arithmetic core for addition is shown in this figure. And the subtraction operation also performed by addition arithmetic core only. Now coming to this multiplication of floating point numbers is made in 4 steps. First, the normalized operands mantissas are multiplied using an unsigned integer multiplier. You can very well get to know that from this flowchart itself. I'm just explaining this in very few and simple words. So, the 4 steps consist of, as I've already said, first, the normalized operands mantissas are multiplied using an unsigned integer multiplier. Second, the operand's exponents are added and the result is subtracted with excess exponent offsets. Third, the output sign is computed using the XNOR operation of the sign bits of the 2 input operands. Fourth, the resultant of the multiplication is then normalized and the mantissa and the exponent of the results are adjusted. The post-normalization of mantissa of floating point numbers is always performed to retain as many significant digits as possible for consequential floating point operations, and the normalization of mantissa is done through shift and rounding control operations. So this is it. You can see the architecture of floating point operation, like multiplication operation and the division operation. So this is it. And both these flowcharts, I'm again saying you can follow draw.io software. It is also a very user-friendly software, or else you can use this Lucidchart, and it is very, I'm always saying it is a user-friendly software every time. And one more thing, the multiplication procedure can be used to perform division on operand where the exponents of the operands are subtracted in division. Note this point. I repeat, the multiplication procedure can be used to perform division on operand but the exponents of the operands are subtracted in division, and the architecture of the arithmetic core for the multiplication and division, they are as well both shown in figure 2 and 3. So, as we already know, coming to this third question, some tabulated results. I have also posted some tabulated results and graphs regarding this report. And floating point data computing is actually a real numbering system that deals with a wide spread of number representation. The floating point numbers, they are fixed number with consequent digits, scaled by an exponent of base 2, 10, and 16. The typical floating point number can be represented as consequent digits multiplied by base exponent. And wide range of floating point numbers has got significant demand due to computer revolution in human life. And the FPU presented in my report, it considers a single precision IEEE 754 data formats and handles floating point arithmetic operations such as addition and subtraction and multiplication and division. Single precision floating point format IEEE 754 standard have 3 basic fields: sign, exponent, and mantissa. sign of a number is represented using 1 bit, and if sign bit 0 indicates positive number, whereas 1 indicates your negative number, an exponent of a number is represented as 8-bit field in IEEE 754 single precision format and represents the exponent magnitude up to 127. The magnitude of a number is represented as mantissa of size 23-bit field in IEEE 754 single precision format. The IEEE 754 standard can be used as data formats for the operations like data interchange, rounding, exceptional handling operations. So that's what I have posted these tables for. So this is the format for IEEE standard of floating point number. So these are all the parameters given and the formats regarding the single precision and double precision, and this is it. And regarding this report analysis of this energy efficient floating point unit, the related pie charts have also been posted using appropriate software. So this is the architecture of floating point unit, which I've already discussed. That obviously ALU operates only on integer values when forced to work on decimal values. It leads to the loss of precision, and hence the floating point ALU is designed to represent large range of values. And I have discussed all these things in the very beginning. And this is the transistor level diagram regarding this report. It shows a dual rail WCHP pipeline along with a transistor level depiction of a 2-input C element gate, which is used in WCHP template. Now coming to the very important question, the most important questions proposed. We need to compare the proposed architecture with existing architecture given in our reference books or articles. So obviously this FPU architecture has been implemented on FPGA, wherein the VHDL is used to describe the behavior of the FPU, and the section demonstrates that the implementation scheme and architectural parameters for performing the floating point arithmetic operations, and what the architectural behavior of the FPU has been realized using the VHDL, appropriate VHDL. The floating point operations, they are performed by providing 32-bit input in the format of IEEE 754, and the operations are selected by providing suitable FPU control signals. The output of the FPU is a 32-bit in the format of IEEE 754, and also flags that describe the status of the operation and exception. And the required output precision can be achieved by selecting some suitable rounding modes. So now coming to the advantages of the proposed design over the existing design. Obviously, it can speed up the execution of the mixed precision applications. One kind, it can speed up the execution. Then it can provide the energy efficient, high speed and precision data. Then the application has very high arithmetic intensity, or the new low power memory technology is also created, and due to this floating point system performance will be limited by memory power. So this goes on like this. The same merits and demerits of the proposed and existing techniques are hardware 53% faster than the Vedic multiplier, 22% faster than the Radix 8-volt multiplier, 18% faster than the Radix 16-volt multiplier, and it consumes less power, reduced delay in operations, performance boost, better accuracy, provides a very large range. And so on. It goes the demerits, applications being the DSP applications, then machine learning algorithms and applications, trans-precision application, then mostly commonly found in application signal processing or SVM, and it goes on like this. This is the flowchart register level diagram again for the single precision cascade multiply add. So this is it. So now I'm going to conclude that proposed FPU has been described, verified, synthesized, and implemented successfully on this device, and the FPU architecture has achieved the requirements of the DSP application service A. And the FPU proposed architecture can be expanded easily without affecting the system behavior by simple method of cell instantiation. So the proposed architecture can provide the energy efficient, high speed and precision data processing for most of the multimedia applications. So this is it. Thank you and have a nice day.